I think so. Good morning to everybody. Now, only the 25 participants have been joined for the online session. Shall I minimize this window? So nice to meet you again. This is the year 1 semester 2 module, mathematics 2 ICT. We have already completed the first year module, mathematics 2 ICT 1. That the knowledge you have obtained from that module will help you to understand the units under the mathematics 2 ICT 2. Let me initially explain what are the units we are supposed to cover under the mathematics 2 ICT 2. The first unit is the complex numbers, and the second unit is the probability and the probability distributions. The third unit is the differentiation, that is the calculus. Then again the integration, that is also belongs to the calculus. And the final unit is the vector algebra. Those are the 5 units included in the syllabus under the mathematics ICT2. I think now we better to start. The time may be limited, even though we assigned the 3 hours, because the Zoom allow maybe 40 minutes for the one session. Actually, still we have been conducting this session on pilot basis because there are some barriers to be solved. You're already aware of these matters. Another thing I just want to highlight before we start the lecture, the material, the reference material will be available on the university website under the LMS for the Google Classroom. Those PowerPoint slides are available. Those slides you can get a printout. When you print in the document, better to have 2 slides per page, otherwise you'll not be able to see the small characters. That kind of thing you can have, right? We shall admit there are some 6 people waiting. Okay, shall we start the unit, the first one, the complex numbers? I just want to start in the slide show view. Now it is open the slide show view. You shall start with the very elementary thing. I supposed to explain everything right from the beginning. So in this online session, everybody should be able to understand and go ahead. That is the way to see this, to understand this module. The time to time, the students are registering. The number system. The first number system is what we call the positive integers. The number you are already familiar, 1, 2, 3, 4, 5, and so on. Positive integers. Sometimes we call the counting numbers, and so on. Then the positive and negative integers. That is -3, -2, -1. All the negative integers and all the positive integers included. And we denoted these positive and negative integers as Z. Then come to the rational numbers. Rational numbers, you see the numbers can be converted in the form of P divided by Q, like a fraction, The P element of Z and Q element of Z. The P and Q can be come from the Z set, negative, positive integers. See some examples are given. Sometimes the content cannot be visible because of this. Right. You can see the content, the rational numbers. the minus 5 minus 4 by 3, 9 by 4, 23 by 4, 41, 9 by 2, 2. And all the numbers, simply we call the rational numbers. The numbers can be expressed in the way P divided by Q. Next number set is the real numbers. You see here the real number. What is the real number? That include all above. All above means the real numbers include all positive integers, positive negative integers, or rational numbers. But in addition, there are certain numbers, specific numbers included under the real numbers. You see the square root of 7. Square root of 7, all the square root, right? And the pi and the e. What is the main feature of these numbers? It is an infinite number of decimal places. Now, for example, if you use the calculator to calculate the square root of 7, that is, you get 2 point something. The decimal places are infinite. Like the pi also, the familiar is 3.14. Approximate value is 22 upon 7. That is only the approximate rational number, but it's again infinite decimal number. E also the exponential value. You are already familiar. Even first semester we have discussed 2.71 and so on, infinite numbers. You see now it is clear what is the real numbers. All the numbers n, z, and q, but in addition, you get some infinite numbers, square root of 7, square root of 17, whatever all the square root numbers and the pi, e, etc. Finally, we get the complex numbers. Now you can understand the complex numbers included all above. All above mean all n, z, q, r, but you can see in addition there are some special numbers there. Square root of minus 4, square root of minus 5, square root of minus 17, and so on. Some people are still waiting. I think everybody can understand. If you have any question, you can raise a question quickly. It is very straightforward. Now, what is the most important thing to understand at this stage? Now our topic is the complex number. That means any of the numbers what you are already familiar, either positive integers, positive negative integers, or rational numbers, real numbers, all belongs to the complex numbers. But in addition, there are some imaginary numbers called square root of minus 4, square root of minus 5. All the square root of minus numbers belongs to the complex numbers. The next slide, you see the graphical representation of the number system. Outer circle represent the complex numbers. You see the inside the complex number set, all the numbers are included. This is how we represent the number system in graphical form. Now, most important thing at this stage to understand the complex number includes all the number system that you already familiar, but it has some special numbers, what is square root of minus number, right? Now, let us discuss what is the square root of minus 1, right? It could be square root of minus 3, square root of minus 4, minus 5, whatever the number, right? Let us take this particular equation, x squared minus 1 equals 0. If you rewrite it, it will give x squared plus 1. And this is very simple because x equal is square root of 1. Then so x equal actually square root of 1 mean plus or minus 1. Why we get the plus or minus? If you get the square 1 squared or minus squared, you get the 1. Therefore, it has the two roots, x equal 1, x equal minus 1. Now we come to the very important equation related to this particular topic. Now consider the equation x squared plus 1 equals 0. That gives x squared equal minus 1. Then x equal square root of minus 1. So x equal, again we get the two values, plus square root of minus 1, x equal minus square root of minus 1. Those are the roots actually we call imaginary roots. Square root of minus 1 is the imaginary root. In mathematics, normally this square root of minus 1 is denoted by simple j. Actually, the square root of minus 1 can be denoted in two ways. One is the simple I. The normally advanced mathematics is square root of minus 1 denoted by simple I, but in general mathematics, normally we denoted square root of minus 1 as simple j. If you see in a textbook, I or j, no different. Remember, no different. I, it could be sometimes I, it could be sometimes j. Meaning is square root of minus 1. So now we can write the roots of the equation. But the equation x squared plus 1 equals 0. You get the roots x equal plus or minus j, or x equal plus j, or x equal minus j. Right. Shall we go to the next slide? Finally, we see there's some explanation there at the bottom of the screen. The two imaginary roots plus j and minus j. So let us take another quadratic equation. Now you are already familiar with this kind of equation because we have done in the first semester how to solve this kind of equation. I think if you can remember, we have discussed actually four methods. No, four methods. One method, if the factors available, you can factorize equation, or using the graphical method, you can solve the equation. Another one is complete in square method, and then using the formula. Actually, it has four methods. Remember, now we have been discussing the equation, no real roots. It has only imaginary roots because the topic is the complex number. Can you factorize? No, you can't. Use complete in square method or formula. You know that the two methods available to solve the equation. If you use the complete in square method, I think you can remember we have been discussed these matters in the first semester. Now, what is the mechanism? Find out the coefficient of the x terms, that is the minus 2, divide by 2, you get minus 1. Then you can write the first statement equation equal x minus 1 squared minus 1 plus 5 equals 0. If you simplify, you get the first equation. X minus 1 squared means x squared minus 2x plus 1. Then plus 1 minus 1 will be cancelled. Plus 5, you get the same value. This is much easier to solve. This will give the x minus 1 squared plus 1 equals 0. Then x minus 1 squared equal minus 4. Now you get the x minus 1 equal plus or minus square root of minus 4. The square root of minus 4 can be divided into two parts. Minus 1 times 4. Then separate the square roots. Square root of minus 1, square root of 4. Finally, you get the answer plus or minus 2. That is the square root of 4. My square root of minus 1, normally we denote it as j. You get plus or minus j. That is equal x minus 1. Therefore, x equal, you can get the minus 1 to the other side. 1 plus or minus 2j. Now you get the two values here. X equal 1 plus 2j. X equal 1 minus 2j. You see, this particular two solutions we call the pure complex numbers because it has the both parts. The 1 plus 2j imaginary part and real part. I think we can understand. I think I asked you to bring some papers and pen with you. You have to do some calculation as I mentioned. I will give you some exercise to practice, task to students. Now take this, write down this equation. X squared minus 2x plus 2 equals 0. and find the complex roots using the completing square method or formula. Now you are free to choose any of the method, either the completing square method we explained early, and the formula also we can use to find out the complex root. I will give you 5 minutes to work out on this question, right? Now start yourself. If you want to ask a question, that you can switch on your microphone and tell me, right? You can raise a question if you want. Just one by one we have to do that, right? Just switch on your microphone. You can tell me the even answer if you finish. The time to time, I just want to make sure everybody can hear me. I think we have been conducting these lectures on pilot basis because we have to make sure everybody can follow the lecture. Those who finish, you can tell the correct answer. There are 2 roots, of course. So this is the kind of interactive session. Those who have completed, tell me the answer. Do we need any more time? Nobody responds.
X equal to 1 plus j or x equal to 1 minus j.
Yes, good. Let us see the answers. We can't wait so long because they have to be very careful because whether we have some doubt because this session can be winding up within 40 minutes sometime. It depends on those are some trial versions. So see the solutions. First completing square method, x minus 1 squared minus 1 plus 2 equals 0. Then simplify, you get x minus 1 is squared is equal minus 1. So that is equal plus or minus j. So therefore x equal 1 plus j and or x equal 1 minus j. The answer given is correct, right? Thank you. Now, if you want to see the other method, the using formula, I think in DC O level also you have been practicing these methods. Yeah, A equal 1, B equal minus 2, C equal 2. You can realize here the completing square method is still simple method, to get the solution like that, which is a bit difficult, but you can see the answer here. The formula x equal, this is a standard formula, just substitute the values. I'm not going to explain each step here, you can understand what is here. Then you see the final answer, you get the same answer, see? 2 plus or minus 2j divided by 2, again 1 plus or minus j. Whatever the correct method you use, you will get the correct answer, right? 1 plus j, 1 minus j, right? Now we go to still we have this one very elementary thing, I think everybody can understand easily. Now we, the common form of the complex numbers, this is some of the answers for the previous lesson. Now, any expression of the form a plus jb, where a and b are real numbers, positive or negative. Remember the a or b, a and b can be either negative or positive. is called a complex number. This is what we call the general form. Later we give a proper name, a Cartesian form. A plus JB. A is a real number. B is a real number. It could be sometimes negative, positive. You know what is the real number. It could be a integer, or the rational numbers, whatever like that. As you will see later in this course, they have been found to be huge importance in mathematical analysis in many engineering systems, particularly the alternative current theories in engineering. The complex numbers heavily involved. In ICT also, there are so many areas where this complex number will apply. Now go to the general form, which is called the Cartesian form of the complex numbers, right? How we define. As we said, given any two real numbers, A and B, you can specify a complex number. It's a common practice to use Z to denote such expression. Then we write Z equal A plus JB. Actually, the Cartesian form of the complex number, it has the two parts, real part and the imaginary part. A normally we call the real part, B called the imaginary part. Actually, the both A, B real, remember, only the different here, J. J is the imaginary number, is square root of -1 every time. Right. And you see the definition there. It's called the Cartesian form of the complex number. Simple A is called the real part of Z. B is called the imaginary part of Z. Those are, I think, very straightforward concepts. This is very just the beginning, the start of the complex numbers, right? Notice the important thing there. Notice that J is not included in the definition of the imaginary part. That is all. The A is the real part, B is the imaginary part. Even though we call B is imaginary, actually both A, B are real. Because we call imaginary part, that is associated with the J. That's the only difference. I will give you some example to understand. Let us see this number 2. Can you remember when we define the complex number? All Z, all N, all rational number, that is Q, all R belongs to the complex number because of this now. What is the number 2? Number 2 equal, if you convert into the A plus JB form, 2 plus J0. This is again complex number because J component is 0. The time to I have to admit some students because they're latecomers, right? That is to be called the pure real number. Another pure real number, -5. -5 plus J0. Because you see, the first example, A is 2, B is 0. Second one, A is -5, B is 0. Second one, even decimal number is a complex number. 0.7 plus J0, pure real again. Another pure real one, a fraction, 2 by 3. 2 by 3 plus J0. Now you see the pure imaginary number, J2. J2 means A is 0, B is 2, A plus JB. So like that. Now you can understand any number can be converted to a complex number. Sometimes it could be a pure real, sometimes it could be a pure imaginary, or sometimes both parts may be included. You see still the pure imaginary numbers. The final one you see there has both real and imaginary part. 2 plus J5. I think now you can understand the very elementary concepts regarding the complex numbers. Sometimes the number pure real, sometimes the pure imaginary, sometimes both parts included, the common Cartesian form of the complex number. The final one, see, 2 plus J5. Just want to make sure the time also because 20 minutes, right? Now we discuss the mathematical operation on complex numbers. I think you are already familiar the mathematical operation on other numbers because real numbers, rational numbers, we are familiar algebra first semester. Now we have done so many operations. Now we come to the topic now, mathematical operation on complex numbers or rules. Let us take first one, the two complex numbers, Z1, A plus JB. Z2 C plus JD. Where B, C, D are given real numbers. Equality. Initially, we discussed the equality. How do we define the what is the condition to be satisfied? For example, two complex numbers are equal. Two complex numbers are equal if and only if the real parts are equal and imaginary parts are equal. That's the rule. You can see here. Given that Z1 is Z2, then sorry, there's a mistake there. I'll have to correct it, right? There's a mistake there. Only A equals C, B equal D. There's some mistake there, right? I'll correct it later, right? You can understand it easily. Real parts are A equal C, B equal D. There's some mistake, typing mistake there, right? Correct. So addition can be defined like this: Z1 plus Z2. First write the two complex numbers, A plus JB, C plus JD. What is the mechanism? Add the real parts together, A plus C, then J times B plus D. If you know the A, B, C, D values, actually addition also become a complex number in the form of Cartesian form, like A plus C is a number plus J times a real number. Likewise, right? A plus, that's also A plus JB form. Then the subtraction also same. The real parts has to be separately simplified. Imaginary part should be separately simplified. You get A minus C plus J times B minus D. Come to the multiplication of the complex numbers. It's very interesting now. I think you know, you are familiar how to multiply A plus B, C plus D. Same pattern you can apply here. A plus JB multiplied by C plus JD. Now we have to multiply four terms. No? A times C, AC. Then you get JAD, JBC. Interesting thing is, once you multiply the JB and JD, you get J squared BD. J squared BD. What is J squared? Actually, we'll be discussing this matter in the next couple of slides. J is the square root of -1. Therefore, J squared is a -1. Therefore, J squared BD means minus BD. Then you can combine AC and BD together. That's the real part. Then you can take the J out from the other middle terms. You get AD plus BC. Now you see again here, the product also in the form of the Cartesian form, A plus JB. Here AC minus BD is a real part. AD plus BC is the imaginary part, likewise. Now before we come to the division of the complex number, there's a certain concepts to be familiar. That is what you call the complex conjugate. Right? Before proceeding to division, we need to define, now see the new term, complex conjugate, very important in complex numbers. What is the complex conjugate? Now we discuss that particular one, very simple. If you have a complex number Z equal A plus JB, and complex conjugate is denoted by Z bar. You can see the small dash on top of the Z there. That is called Z bar, a conjugate. That is equal A minus JB. What is the difference there? The plus mark become minus. Plus mark become minus. Remember, very important here, in addition to this, AB can be sometimes plus or minus. You have to be very careful, because when you finding out the conjugate, because AB sometimes could be negative or positive. Now here you see the A plus JB, that is Z bar is A minus JB. Here another thing you have to understand, here we describe Z bar is a complex conjugate of Z. Other way also we can define Z is a complex conjugate of Z bar. Can you understand that? Z bar normally we call complex conjugate of Z. Z we can call complex conjugate of Z bar. Both ways we can tell like that. Right? Let us see some example. That is next. Are called the complex conjugates. See the complex are called the complex conjugates. That's the reason I mentioned. Z bar is a complex conjugate of Z. Z is a complex conjugate of Z bar. That's what we define. Are called Z and Z bar called complex conjugates of each other. Remember, this is a very not is a like a spirit. No additional information is being given. Only the required information is given. Conjugates of each other. They have a special property with regard to the multiplication as follows. Now see some special properties of the complex conjugate. Right. Now see, if you multiply Z and Z bar, that is A plus JB, A minus JB. You know, the first semester we have been discussing this kind of multiplication where is, you know, the so many times. You see that? Again, you get 4 times A squared JBA minus JAB, then minus J squared B. You see the minus JAB and plus JAB are same. You know, the opposite of 1. So that will be cancelled, like minus 2 plus 2, minus 5 plus 5. Minus JB plus JB will be cancelled. See the what is the J squared is a minus 1, because J is the square root of minus 1. J squared is a minus 1. Therefore, minus J squared is a plus 1. What is the answer finally? A squared plus B squared. That is the, you know, the mentioned the special property. Once you multiply the complex number by its conjugate, you get the real number. No complex part involved here, because if you multiply Z and Z by, you get the A squared B squared. Remember this result, because frequently you have to use. If you get a complex number in this form, A plus JB, A minus JB, straight away write the answer. What is the answer? A squared plus B squared. That's all. Still some student meeting, right? Latecomers, like in the class. Right. The product is a real number. This is very important result which you should memorize. Okay. See some examples. 2 plus J5, 2 minus J5. Straight away write the answer. 2 squared plus 5 squared. It doesn't matter whatever the either, you know, the AB could be negative or positive. Straight away get the 2 squared, 5 squared. Whether it's a negative, you get the plus number every time. That's a positive real number. 3 minus J4, 3 plus J4. What is the answer? 3 squared plus 4 squared. That is 25. This rule is, this is used in division in the following way. So this has been used here for the division of the complex numbers. Now, right, now come to the division now. Z1 divided by Z2. That is A plus JB, C plus JD. Remember now, so far, addition is a complex number, subtraction also a complex number, multiplication of a complex number. Now we see, is it possible to convert this particular expression, A plus JB, C plus JD, in the form of real part plus J times imaginary part, right? What is the mechanism normally we use? You see the mechanism also specified here. We multiply both numerator and the denominator by the complex conjugate of the denominator. That the denominator here, C plus JD. The complex conjugate of C plus JD means C minus JD. C minus JD. Now see the next slide, you can see. Still in this slide, right? Z1 equal Z2 equal A plus JB divided by C plus JD. Multiply both sides by C minus JD. Why we multiplying this one? Because the bottom part is become a real number. C squared plus J squared. When you multiply the above the top part, you get the 4 terms, then combine and separate. Finally, you get the answer. The real part is AC plus BD divided by the C squared plus D squared. j times bc minus ad divided by c squared plus d squared. What is this final answer? It's like a plus jb form. AC plus b divided by c squared plus d squared, the one real part. Other real part is bc minus ad divided by squared plus d squared. Let us see one example, then you can understand. Right. This I think we have discussed it. Everything. Start with the addition. Same example, right? That this is 2 plus j5. This is 1 plus j4. Two different complex numbers. Let us add the two complex numbers. Addition. Add the real part. 2 plus 1, 3. This is very simple. J5 plus J4, J9. You know, sometimes remember the J5, 5J, no different. Right and sign is there. J5 or 5J, no difference. The 5J plus 4J means 9J. Or J5 plus J4 is 9J. Likewise. This addition. Subtraction, no different. 2 minus 1, 1. 5 minus 4. Again 1 j, so final answer is 1 plus 1. You have to be very careful when you remove the brackets. Notice the sign will be changed, the minus 4j. When you remove the brackets, the sign will be changed inside. That is the division, subtraction. It's not moving. All right. Right. The machine little bit stuck. See the multiplication. Same complex numbers. 2 plus j5, 1 plus j4. When you multiply, you get 4 terms. See, 2 times 1, 2. J5 times 1, j5. 2 times j4, you get j8. The final term, j squared 20. 5 times 4, 20. J squared 20. Now simplify. Adding like terms, you get 2. J5, j8, 13j. J squared is a minus 1 again, minus 20. Then you can combine the two first term and the second term, last term. That's minus 18. And plus j13. That is the final answer. You see the final answer also become a plus jb form. Okay, now. Actually, yes, another example is given for the multiplication, right? Another example is given. So done is 2, this time 2 minus j3, 1 plus j5, multiply 2 minus j3 plus j10, then minus j squared 15, because minus multiplied by plus minus j times j squared 15. Simplify, you get 2, 7j, j squared is a minus 1, minus j squared is a plus 1. You get the plus 15 there, plus 15. Then finally you get the answer 17 plus j7. You see the final answer like in the form of a Cartesian. Right? Then we go to the the application slides. Wait and see. Right. Now see the division. Now this is the same two complex numbers. Z1 divided by Z2, 2 plus J5, 1 plus J4. What is the mechanism? Multiply both sides by 1 minus J4. Remember this every time when you divide the two complex numbers, you know what is the complex number just below the line, 1 plus j4, multiply both sides by the complex conjugate of 1 plus j4. That is normally denominator, right? You see the results now. Just multiply both sides 1 minus j4, 1 minus j4. So bottom side you get 1 square plus 4 square. Right? Then top product, so you get 4 terms when you multiply 2j5 minus j8 minus j square 20. And when you simplify, you get the final answer 22 upon 17 minus j times 3 divided by 70. You won't get every time the integer answers. You know, when you divide the complex numbers, usually you get, there's some rational form of real part, rational form of imaginary part. You see that 22 upon 7 is a rational number, but in a real number, right? This one. Now this is a kind of exercise, give you some time, like in the previous question. Draw your attention now, everybody, right? Task to students, the two complex numbers are given. 1 plus j2, 2 minus j. He said 1 is a 1 plus j2. He said 2 is a 2 minus j. Find addition, subtraction, multiplication, and division. I'll give you some time. The better to understand and go ahead. That's better, other than just the listening to what I'm telling, right? Just to take a piece of paper and pen, just work out on this simple question. Addition of the two complex numbers and subtraction, multiplication, and the division. Division might take some time, but try to complete at least 3 within 5-10 minutes. If you have any question, just you can raise, right? So done the first part, you can take your answer. 1 plus j2 plus 2 minus j at the real parts. 1 plus 2, 3. j2 minus j, that is j. The answer is 3 plus j. So far, I think it's very straightforward. You can understand easily. Similarly, the subtraction can take your answers. 1 minus 2 minus 1. j2 plus, remember here when you remove the brackets, the final j become a plus j. 2j plus j, 3j. The subtraction is z1 minus z2 equal minus 1 plus j3. I think I assume everybody get the correct answer. Let us go for the multiplication. the multiplication of the same two complex numbers. If you multiply, you get the 4 terms. 1 j4 minus j squared 2. I think take your answers, right? Simplify 2 minus j4 minus j minus plus j3. Remember again, j squared is a minus 1. So therefore minus j squared is a plus 1 plus 2. Then 2 plus 2, 4. The final answer is 4 plus j3. This is very interesting. See that when you multiply the two complex numbers, final result again become a complex number in the form of a Cartesian a plus jb form. You got the correct answers? That's all done. No response from anybody? You did it? Can you hear me?
Yes, yes.
Okay, right, good. Finally, we go for the division. Remember, this is a very important part because some students do mistakes here. I know some past experience, many students do mistakes in the division. See the division, 1 plus j2, 2 minus j. You know, you have to multiply both sides by the complex conjugate of 2 minus j. What is the complex conjugate of 2 minus j? What is the complex conjugate of 2 minus j?
2 plus j.
2 plus
J.
Oh, yeah, very good. 2 plus j. Multiply both sides by 2 plus j. You see? Then the bottom side, you know, the a plus b, a minus b, a plus jb, a minus jb, a square plus b square. Remember that one every time. 2 square plus 1 square. That is 5. The above product, very interesting here. You see the 2 j4 plus j squared 2. J squared is a minus 1, minus 2. You see the 2 and 2 cancel. Actually, in this final answer, the real part become a 0. The j5 by 5, you get j. And actually, finally, you know, it will simplify to the final answer, the complex number j. J is a complex number because the real part is 0. What is the complex number? 0 plus 1j. A is 0, B is 1. Remember, B is not J, B is 1. So those are the matters we have to be very careful. Once you get the complex number, finally 0 plus J, B is not equal to J, A plus JB. B is 1. 1 times J, 1. Therefore, here A equals 0, B equal 1. Notice that, right? I think now we have come to the conclusion of some first part. Now we go for the very interesting in engineering, the powers of J. Powers of J. Let us take one. Start, right? J equal square root of minus 1. This is the, we have started from this one. What is J squared? J squared is a minus 1. That is also very simple. J squared is a minus 1. If you want to calculate the further powers, use the above. Now, for example, here, J3 means J squared times J. But J squared is a minus 1. Minus 1 times J. So, minus J. So, what is J3? J3 is a minus J. Remember now, J squared is a minus 1. J3 is a minus J. What is J4 now? Sorry, we have got additional one. Leave it right there. Still student right. J4 is a J3 times J. What is J3? Above result J minus J times J minus J squared. J squared is a minus 1, therefore minus 1 plus 1. Now you see the final result. J4 is the 1 again. What is J5? J5 means J4 times J. That is J4 is 1 times J. J5 is J. Now what is interesting thing here? Now if you calculate further powers, 6, 7, 8, 9, 10, you get the same answer. Same answer means the answer either 1, either minus 1, either plus J or minus J. So what are the values so far we get? See the j squared minus 1, j3 minus j, j4 1, j5 j. See the all the values are there. Minus 1 plus 1, j and minus j. Let us see what is j6 now. Wait and see the response and the question is little bit.
So can you explain again this slide?
This four lines. Okay.
Yes.
If you have a question, please raise. Right. I'll explain it again. Let's explain it again. Now, can j is the square root of minus 1, no?
Yes.
J is the square root of minus 1. What is j squared then? J squared means minus 1.
Minus
So
1.
far we have been using, for example, we have actually obtained this minus 1 from the equation x squared equal minus 1. Can you remember? X squared equal minus 1. So x equal plus or minus the square root of minus 1. That is j. So j squared is a minus 1. Now, if you want to calculate the j3, what is j3? j3 means j to the power 2 multiplied by j to the power 1. Simple indexes, no? Simple indexes. But we know the j squared value, that is minus 1. The minus 1 times j equal minus j. So similarly, if you want to calculate the j4, j4 can be j3 times j. That is simple, no? Simple index j3 times j1. That is j4. j3 is a minus j. Minus j times j means minus j squared. J squared, we know the value minus 1. Minus 1 is a 1 again. So finally, similarly, you get j5 also, j. Now we go for the other values. I don't know the there is. It's not navigating the other slides. So let us wait and see. Maybe because of the, I don't know, because of this.
We use previous result for current steps.
Sorry?
In the current result, we use previous step and
Yeah,
get answer.
every time we use the previous results. For example, if you want to get the J, we use the J2 value. If you want to get the J4, we use if you want to get the J5 value, we use the J4 previous value. If you see the screen, you can see it later. You know, I am finding it difficult to navigate the screen because the machine is stuck. Now just try to scroll the, now this has been, we have been discussing here, no? J squared minus 1, j3 is minus j, j4 minus 1. This is the place where I stop early. Everybody can see the screen now?
Yes.
Yes, yes,
Can you see the screen now?
Yes,
yes,
sir.
Okay, okay, we continue. Now,
Yes.
next one, sorry? The next, the j6, see the j6 is j5 minus j. j6 is j5 minus j. j5 is the j. The previous result every time we use j times j squared. Now you see the again minus 1. So subsequently you see the other result j7 minus j. j8 minus 1. This is a cycle. Can you notice this is a cycle? Minus 1. Start with the j squared. Minus 1 minus j. 1 j minus 1 minus j1. Right? Remember the powers of j, whatever the power, normally you get the values from that particular set. What is the set? Either plus or minus 1 or plus or minus j. In the next slide, you can see it very clearly, the cycle. See? In black color, you see the powers j squared, j3, j4. Out of the circle, the results. j squared minus 1, j3 minus j, j4 1, j5, again j5 become again j, j6 minus 1, see, j6 minus 1, j7 minus j, j8 again 1. This is then being continued, like a cycle. Whatever the power of j, you get, the 4 results actually, either plus or minus 1, either plus or minus j, right? Is it clear to everybody?
Yes.
Now we go for the, when you do some further calculation, under the what we call the polar form next lesson, frequently use this, the powers of the j. These are very interesting. Now see the negative powers. Similarly, we can find out the negative powers of the j also. Now see the minus j to the power minus 1. I'll slowly explain, right? What is j to the power minus 1? That is 1 upon j. Now see 1 upon j is like, the division of the complex numbers again. Multiply both sides by complex conjugate, actually should be multiplied by minus j, but even though you multiply by j also, you get the result, no harm. See, if you multiply both sides by j, the top, that is j, the bottom j squared is minus 1, see minus j. So what is the j to the power minus 1? That is minus j. So similarly, you can calculate minus j to the power minus 2. That is 1 upon j square. Now use the previous results. Sorry, j square we already familiar, j square is a minus 1. So that is minus 1. What is j to the power minus 3? 1 upon j3. Now use the j3 earlier. j3 is a minus j. So 1 upon minus j. So 1 upon minus j. Now we have the result 1 upon minus j is a minus j. So minus j is a j. Again, you see the very interesting result. Again, also we are getting the values, the same values. Either plus or minus 1, plus or minus j. See, j minus is a minus j squared is a minus 1, j3 minus j to the power minus 3 is j, j4 is 1. Or similarly, you get, the j5 is a minus j, j6 is a minus 1. Similarly, you see the same cycle you get. The values are different actually. J to the power minus 2 is a minus 1. J to the power minus 3 is a j. J to the power minus 4 again 1. Similarly, the cycle will continue. Now I think there are some solved problems. If the time permits, we will continue. This part also simplify complex numbers. Some worked examples. Now, if you have a piece of paper, you can do yourself first. Then I can give you the answers. The simplify complex number, like the simplify algebraic expressions. Like terms can be added. Now, for example, you see the addition of the two complex numbers. First one, you can straight away write the result. Add the real parts together. Add the imaginary parts together. Do it in few minutes quickly. Remember, when you are adding, remember every time you have to add the real parts together, imaginary parts together. I think time is enough for this exercise. Let's see the results now. Just disturb the answer now. You see the results now. The first one is the 5 plus 2i. Remember, I and j are different, right? Because this has been taken from the textbook itself. The I no different. I and j both same, right? The second one answer is 9 plus 5i. The final one, when you remove the brackets, minus 4 minus 5i. So minus 4 plus 2i. Remember, I or j no different, right? You can understand easily this. Then the multiplication. Simple example, you can just multiply and try yourself. Even this is in something like a classroom, face to face, because we have to do some exercise and understand and go it. Otherwise, by looking at the screen, you will not be able to learn. You must do even simple activities. to understand the basic concept. Still remember, we have been discussing very elementary thing on complex numbers, right? Just multiply the A, B, and C. A is a very simple. Just multiply by 3, like we simplify algebraic expressions. Third one, you get the 4 terms to be multiplied. I think now we can go for the answers now. This is the first answer. 6 plus 12i. Second one, you get 5i, then 3i squared. I squared is a -1 every time. So 5i minus 3. When you are writing the complex number every time, remember writing the real part first. That's another important thing to notice. Writing down the complex number, don't write the imaginary part first. The second answer is the -3 plus 5joi. There's a final one. There's four terms when you multiply 2 times 3, 7 minus 7i times 3, and so on. You can understand. Again, you get the minus. I squared is a -1. Therefore, final part is plus 28. Finally, you should get the answer 34 minus 13 JOI. Is it okay? Shall we proceed? Okay. Can you hear me?
Yes, yes.
Okay. Now division. You have to just do it, do and understand. Go ahead. Division. Another simple examples. Simplify the following: 1 upon JOI, 3 divided by 1 plus I, 7 plus 7i divided by 2 plus 5i. You see the instruction also given as I mentioned earlier. See the bottom of the screen. Just to simplify this expression, you multiply the numerator and denominator, right? Numerator of the quotient by the complex conjugate of the denominator, right? The quotient by the complex conjugate of the denominator. Denominator is the first one is I, second one is 1 plus I, third one is 2 plus 5i. Multiply both sides by complex conjugate of the denominator. At the same time, you can see the answers also. This is the first one. Multiply by minus I or G. This is the second one. The complex conjugate of 1 plus I is 1 minus I. Then simplify. Answer is 3 by 2 minus 3 by 2 JOI. That is the solution for the first two parts.
Okay.
Shall we proceed now? The third part.
Yes.
Third part. Multiply both sides by the complex conjugate of the 2 plus 5i, that's 2 minus 5i, then simplify. You multiply 4 terms. All the simplification steps are not given here, but you can understand. 4, 3 minus 6i divided by 29. They have to separate the real part and imaginary part and get the answer similar to this. I think I don't know that we have the printout of this material. From the website, I think you can download. If you can't download, tell me. I can forward to your common mail this material, and better to keep some hard copies, because are you having some hard copies of this material?
Yes.
That's good. That's good. Otherwise, we have to have separate reference material with even the online deliver. Sometimes you will not be able to understand everything. That you need to some reference later on. Okay, we go for the solving equations. These are some application of the complex numbers. Solving equations, the like a simple equation, right? When we solve some simple equation, same aspect can be used even for the complex numbers also. The first one, you can just bring the minus I1 plus 1 minus sign to the left hand side and simplify. That's all you have to do. The part A, the right hand side says Z minus 1 minus I, no. Take the 1 minus I part to the other side. That become a plus 1 minus I, no. Then simplify, then get the Z answer. That's the simplest way to do that. But here we give in this slide, it has another solution also. Go for that particular method I just mentioned. That's easier. The second one is Z equal, what is it? 2 plus 5i divided by 1 plus 2i. Then simplify and then you get the answer, is it? Forgot about the first answer, first part, it's not necessary. This part is not necessary because you cannot. This part is not necessary. This part is not necessary. Just understand the method I just mentioned, the second part. Right? Take the second answer is better. Now the final one. Z equal, like a simple equation, Z equal 2 plus 5i divided by 1 plus 2i, then multiply both sides by the complex conjugate and simplify, you get the 12 by 5 plus 1 upon 5. That is the answer for that particular one. Now these exercises I'm not going to do it now because there are some reference exercises that you have to do leisurely when you get some free time. Start with the the solving some complex equations and simplify some expressions. There's no, I think if you get the hard copies of these things, the better to practice yourself these. Whenever you get the opportunity to discuss the face-to-face session, maybe when this problem is over, we'll be able to discuss these exercise. If you want, these are some exercises. That all the exercise cover all the content so far we have discussed. At the end of the first session, if the software permit, we can go for the next part of the complex numbers. I think the first part is not very difficult. I think very basic concept we have been discussed. Under the Cartesian, only the one form, Cartesian form, with some the mathematical operations, addition, subtraction, multiplication, and division. Those are the not many things we discuss, right? Now in the syllabus you are supposed to familiar the other two forms of the complex number, that is the polar form and the exponential form and the conversions also, right? And some more in Argand diagram, De Moivre theorem, transformation of the complex numbers. We, as the time permits, we try to continue. This is the polar form of the complex numbers. I think everybody can hear me. Polar form of the complex number. Now see this is the Cartesian coordinate system. Here also, I am supposed to explain everything very basically right from the beginning, so that everybody can understand easily these concepts. I think this is the Cartesian system. I think you have been practicing this grade 6 onwards, these things. But this feature, the point can be uniquely defined. Remember, The point can be uniquely defined by two coordinates x and y. But in addition, you see the right hand side, another method is there to uniquely define the point using the distance from the origin and the angle. This is called the polar form. You see the earlier the P point is coordinate x comma y. The second diagram, the polar form, the P is r comma theta. Uniquely defined two methods using xy coordinates or the r and theta, the distance from the origin to the point and the angle measured from the from the x-axis. When any point could be in the second quadrant, third quadrant, fourth quadrant. So likewise, there's a very popular in advanced mathematics. In addition to the Cartesian coordinate system, this polar system is also used. Right, we go for the next slide. I think some images are disturbed. Shall I drag to the right-hand side? Okay. Now see the coordinate system at the bottom of the screen. See the x coordinate, y coordinate. You see here, both the coordinate system has been highlighted, x, y, r, theta. Normally in the coordinate axis, normally we not define as x-axis, y-axis. The x values are normally we call real Z denoted by REZ. Y-axis normally we denoted by imaginary, IMZ. Right? Imaginary values are plotted against the y-axis. Real values are normally plotted against the x-axis. You see the xy coordinates and r theta. Now we go for the students. I still try to admit it. Now see the read the text. There any complex number x plus jy where x, y are real numbers can be represented by a point in a two-dimensional coordinate system as shown in the figure below. You see that the compared to the interesting thing here, the coordinate of the P point is x comma y, right? If you see the definition of the complex number here, Z equal x plus jy. Now we say the P point represents the complex number Z. That is the notation to remember, right? Shall I repeat it? P point represents the complex number Z. Right? If you want to represent the particular point, find out the coordinate x and y. Forget about the j, x and y, right? That is the representation of the complex number on actually this diagram we call the Argand diagram. It will discuss later on, right? So horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. The notation is also there. Then the complex number is represented by the point P. This type of diagram is known as the Argand diagram, right? This type of diagram is special name, right? We call the Argand diagram. In the next slide, you see the very simple, actually example, represent the following complex numbers on Argand diagram. You also can do it, but it's not necessary to try. I'll show you the answer. See the answer to the right hand side. The complex number 3 plus 2i. Remember, it has been taken from the textbook. Therefore, it use the I notation, right? 3 plus 2j, assume 2 plus 2j. Now, what is the point? X is 3, y is 2. You see the point there? X is 3, y is 2. That's in the first quadrant. The second complex number 4 minus 5i. That is in the fourth quadrant. X equal 4, y equal minus 5. You see the points? Then the final one, minus 2 minus I, that is in the third quadrant, x equal 2, minus 2, y equal minus 1. The point is, coordinate is minus 2, minus 1. Actually, you see the 3 points represent the 3 different complex numbers. It's very simple definition. Now, the interesting thing, the proof of not necessary to give at that state proof are very simple state where you can understand easily. Now see the diagram below first. The P point represents the complex number Z1. The Q point represents the complex number Z2. Remember the O is the origin, right? O is the origin. If you complete the parallelogram here, in this parallelogram, see the in this part, I think you can see the laser point now. This particular parallelogram, that is OPRZ. You know, if you plot the point P and Q, you can easily draw this particular parallelogram now. OPRQ. Then R point represent the complex number Z1 plus Z2. You can actually show this one very easily because if the coordinates are given Z1 and Z2, the points are given. If you add this particular S coordinate, you get the S coordinate of the Z1 plus Z2. That can be shown very easily. For the time being, just remember, that if you want to get the addition of the two complex numbers on the Argand diagram, just complete the parallelogram. And in this way, you get the Z1 plus Z2. Similarly, if you complete the other way parallelogram, this one, that is OQPS, then S represent the Z1 minus Z2. See, now you can notice that, and if you take this S and Q, addition will be here. Z1 minus Z2 plus Z2, you get Z1. That also you can see it. No? Remember, this is very important results. Later, this will apply, the addition of the complex numbers in polar form or whatever, when you have questions, so you have to solve questions with the Argand diagram, and this facility can be used. Right, you go for the next one. As can be seen in the position of the point P, also uniquely defined by the value of R length. R is the length of the OP line, and angle T, the P is uniquely defined by the two coordinates, the R and theta. And this gives an alternative way of expressing a given complex number. Remember, very interesting, we have been discussing, that now we are going to express the complex number in terms of R and theta instead of X and Y, right? What is OP? Very simple, Pythagoras theorem. R equal square root of X square plus Y square. Right? Don't ask any question because I think very simple, you can understand how to calculate R in terms of X and Y, just Pythagoras theorem, how to calculate theta. And this is called actually the modulus of the complex number, right? Modulus, and denoted by R equal moduli Z. Observe the pattern here, moduli Z. This is the moduli Z. Similarly, also theta can be calculated, tan theta equal Y by X. Remember, every time when a complex number given as a Z equal X plus JY, the tan theta will be given by Y by X. So theta equal tan inverse Y by X. If you have the calculator, you can calculate the angle there. That is called the argument. Now we have learned the two new terms, right? Modulus and argument of the complex numbers. Modulus is the distance OP, simple R. Argument is the angle measured from the x-axis in positive direction. Remember, x-axis, the what we call the counterclockwise direction. For the time being, remember the counterclockwise direction. We measure the theta, but there are some different methods to measure the angle. We discussed later, right? And I don't like to confuse everything at this stage. For the time being, remember the modulus is the distance, simple R. The argument is the theta. That particular theta, also called the argument. Now, what will be the complex number now? I just go to the next slide. Denoted by ARG, notation also there. Theta equal ARG. Not in that notation. ARG say. Now, very simple trigonometry. What is X? X equal R cos theta. Is it clear? What is the cos theta? Cos theta equal X divided by R. Simple trigonometric ratio, what you have discussed in the first semester, right? Cos theta X divided by R. Cross multiply, you get X equal R cos theta. Similarly, sin theta is Y by R. Cross multiply, you get Y equal R sin theta. Now we have the values for X and Y. Therefore, we can write Z equal, what is X? R cos theta. What is Y? J Y, R sin theta. Now take the R out from the bracket, you get the Z equal R cos theta, J sin theta. This is the polar form of the complex number, right? When expressed in this way, we say that the complex number is in polar form. X plus jy is the Cartesian form. R cos theta j sin theta is called the polar form. Now you see here no x and y involved because the polar form we have to convert everything. You know, you have to write everything in terms of r and theta. What is r? Modulus value. Theta is what is theta? Tell me. What is theta? The previous slide. Can you hear? Can you hear me? Can you hear me?
Yes.
Okay. You know, I just want to make sure time to time whether you have been connected. Okay, right. This is the polar form, right? This is the polar form. Normally, you know, during the class, if you do this kind of thing in the classroom, you know, the first day we will not be able to discuss this kind of thing, right? This online session, you know, one of the advantage, lot of things we can discuss, you know, if we have the printed material, the time can be saved. Time can be saved. Okay, engineers often use this notation. You know, there's a short form. Remember, at the bottom of the screen, you see the R angle notation theta. You know, the complex number is written as R angle notation theta. Actually, the meaning is R cos theta j sin theta. Very famous notation. You know, the simple notation not frequently used. The three things to remember. Clearly, the above process work both ways so that given a complex number in polar form can be written in Cartesian form. Both ways, you know, when the complex number is given in a Cartesian form, you'll be able to convert to polar form. When the complex number given in the polar form, you'll be able to convert to Cartesian form. Is it clear? Very important aspect we have been discussing now, right? The conversion. I think you can remember in the first semester we have done the number system, the decimal system, binary system, hexadecimal and the octa system, and the conversion. We have done 12 kind of conversion. Similar, you know, the concept here, conversion, Cartesian to polar, polar to Cartesian. But remember one that is in the fourth quadrant from complex number P. P represent Z1, Q represent Z2. Modular value Z1 is 2 square, no? That is 8. Square root of 8 means 2 square root of 2. Modular value of Z2 is Z2. Why you are getting 2? Because square root of 3 square is 3, 1 square is 1, 3 plus 1, 4, square root is 2. So argument is a minus 4. First one is Z1. Other one is square root of other one is 30 degrees. On the diagonal you can see, right? On the diagonal you can see. I just you know, write some results. Modular Z1 is a 2 square root of 2. Modular Z2 is a 2. Argument is Z1 is a minus 45 because angle in the other direction. Or otherwise you can say angle is a 350, no problem, right? Argument is Z2 is a 30 degrees. Now take the given information. Z1 is modular Z1 is 3 equals 16. That is given in the first part. And remember, if I go to the previous slide, you see that is given, no? No, that's previous one. Question, you see the question, and you have printed the question. You can see the that's given in the first part, right? So done is at 3 is 16. Divide into 2 bar using formula. Is that what is the modular is done is at 3 mean? Modular is at 1 times modular is at 3. Now we know the modular is at 1, 2 square root of 3 times modulo is square root of 3 is 16. Therefore, you said 3 equals 16 divided by this number. You get the 4 is square root of 2. This is a simple division and no any complex thing involved. Now we calculate the modulo value of Z3, that is 4 is square root of 2. Similarly, you can calculate the argument also. See? Now write the formula for the argument. Z3 by Z2 equal argument 3 minus argument Z3 minus argument Z2. That is given as the 7 pi by 12. Remember, as the give that is given in the question. Answer 7 pi by 12 Z3. Argument Z2 is a we know 30 degrees. That is pi by 6 equal 7 pi by 12. They are pi by 12. And now see the first equation gives the modular value of Z3. Equation 2 gives the argument of Z3. Right? Now finally you get the answer. Then same result has been highlighted as our first statement, second statement. Now you can write the complex form 1 and 2. Z3 equal 4 square root of 2 cos 3 pi by 4 plus j sin 3 pi by 4. If you know the modular value and argument, you can write the complex number j. Now remember, now that's what I mentioned, you have to refresh your trigonometry, know what is the value of the cos 3 pi by 4. The angle is 135, remember. Second quadrant, cosine negative, minus 1 upon square root of 2. Actually cos 135 can minus cos 45. Other one is a sine 3 pi by 4, it's a 1 upon square root of 2. Now you see that to understand these things well, you have to refresh your trigonometry knowledge, what you are discussing the first semester. Because otherwise you have to use the table or calculate, the cos 3 pi by 4, cos 130, cos 135, and sin 135. One is a minus sign, other one is a plus sign, plus value. If you use the calculator, you get the decimal numbers, right? Doesn't matter in examination, you can write whatever the way you want, right? So finally, if you simplify, you get the 4 times minus 1 plus j, because square root 2 has been cancelled. Then finally, third part, you get the answer. If you simplify, you said 3 by Z2, that is actually finally you get the answer minus 2, right? Every time, the waiting room. Now see the example. You can start, of course, first part, right? Actually, this question has been taken from the past papers sometime, right? Not from the ICT, maybe other courses. But initial part, as looks difficult, but as you practice, it's not difficult. See the question, complex numbers given in the Cartesian form. Z1 3 plus J2. Z2 given as the 12 minus J5 divided by Z1. You need not to worry because Z1 is given. No? Then you can easily calculate what is Z2. First you have to do that one. Now if you have some papers, you can do it initially, right? Find Z2 in the form of A plus JB. That's the first part. And you can do it now. Because we have done so many examples in the first session. Division of the complex number. Z2 is a 12 minus J5 divided by 3 plus J2. Simplify and get the answer yourself. Z2, get the answer of the Z2. 12 minus J5. I just show you the start if you want. Diagram is not necessary. This is the first part. Z2 equal. That this is not difficult. Sometimes you feel difficult, but that as you do this kind of thing, you can understand easily. This is the Z2 12 minus J5 divided by 3 plus J2. What is the mechanism? Multiply both sides by the complex conjugate of 3 plus J2. That is 3 minus J2. How many times you have to practice this and see? Just simplify. You know that when the examination questions are sitting, you know, normally you get some simple answers, right? Unlike the rational numbers, you won't get rational number. You see the denominator and the numerator both can be divided by 13. So 26 minus 39j divided by 13. Finally, you get the 2 minus j3. Can you see? 2 minus j3. That is Z2. If you plot the 2 points, P is the 3, 2, that is in the first quadrant. See the diagram below. Z2 represents the Q, point 2, minus 3. Remember, x equal to y equal minus 3. That is in the fourth quadrant. You can see the complex number 2, 3, 2, 2, minus 3. What is in the question? If I go to the previous slide, just want to see the question. See the question. Find Z2. Now, we already done it. Show on the Argand diagram the point P represent Z1, right? And point 2 represent Z2. Plot the 2 points, right? Not difficult because one point is 3, 2, other one is minus 2, 3. No? Already done it. Given that O is the origin, show that OPQ is 90 degrees. That's the one part you have to show, right? I'll go back to the next slides now. Here, see. Now, second part is on the diagram. P point 3, 2, Q point 2, minus 3. If you have very basic geometry knowledge, see that just observe the two triangles. I think everybody follow now. OPM, one triangle. OQL is the other triangle. Can you see? Apart from the the hypotenuse, other sides are 2 and 3 for the both triangles. Because P coordinate 3, 2, other one 2, minus 3. As far as the absolute values are, one triangle has the 2 and 3 distances, other one has the 2 and 3 same. But the positions are different. These are we call similar triangles. Therefore, the angle opposite to the size 2 is alpha. That is also the equal to the alpha in the other triangle also. You can see I just marked the alpha beta. It's not in the triangle alpha beta. Beta is opposite to the side 3 of one triangle. In other triangle also beta opposite to the side 3, right? If you see the first triangle, OPM triangle, alpha plus beta, what is alpha plus beta? Tell me if you know the answer. What is alpha plus beta? Tell me. What is the value of alpha plus beta? Using the OPM triangle. I am asking using the OPM triangle because M angle is a 90 degrees, no? M angle is a 90, MP is a 90 degrees. Therefore, what is alpha plus beta? If you are connected, you will be able to give the answer, right? Anybody? What is alpha plus beta? Still, I can't hear any answer. Are you connected?
90 degrees.
Sorry?
90.
Very good. 90. Alpha plus beta is 90. You are following, no? Very good. Alpha plus beta 90. So what is the OPM? What is the POQ angle then? That is also alpha plus beta, no? That is also alpha plus beta. So therefore, the OPQ is 90 degrees. That's already see the answer on this thing. You can see now. OPM and OQ are similar triangles. Alpha plus beta is 90 degrees. Therefore, POQ angle is 90. Right? I think these are not difficult. Now we have to improve your mathematics knowledge, particularly geometry. I know nowadays very poor knowledge in geometry because I am not blaming to, as I have mentioned so many times, some of the problem in the education system. Everything mixed together, and the like Acharu mathematics method, right? Simple geometry has, they have to improve your knowledge. You can understand in this triangle, because what I'm highlighting is the two triangles are, apart from the hypotenuse, sides are 2 and 3, but they are in a different position, right? Therefore, this alpha beta one triangle is similar to the other triangle alpha beta, because every time the alpha is opposite to the side 2, beta is opposite to the side 3. Therefore, both triangles, I think you can see the angle has been marked alpha beta myself. Remember when I developed this material, because these different characters has to be combined from the formula. It's not easy, like drawing on the board, right? I'll go to the next part. It asking the center of the coordinate of the center. I think coordinate of the center. It's a simple geometry, coordinate geometry. When the 2 points are given, you can calculate the coordinate of the midpoint by addition the x coordinate and divide by 2. By addition the y coordinate divided by 2. 3 plus 2 is 5 divided by 2, 2.5. The x coordinate of the c is 2.5. The y coordinates 2 plus minus 3, that is minus 1 divided by 2 is minus 0.5. So easily you can see the coordinates of the point C, that the center of the circle. Can understand that is the center of the circle, because if the O angle is 90 degrees, actually the PQ is the diameter of the circle. Remember, because the diameter is the circle, because that angle is 90 degrees. The C is the center of the circle, so complex number represents the C is 2.5 minus J C 0.5. Then easily you can calculate the radius of the circle using the again coordinate geometry. When the 2 points are given, then you can calculate the distance by considering the OC. Now it is OC, right? OC is the R. OC is the radius of the circle. O is a 0, 0. C is the particular point. 2.5 minus 0.5. This formula gives the distance OP, that is R, that is approximately 2.54. I think sometimes you find it difficult. Better to go through this when you get the hard copies. Do it. After that, some exercises. After that, there are certain exercises. I think if you get the hard copies, I think you'll be able to do these exercises. You do leisurely, right? You do leisurely. Not difficult. The complex numbers are given. Just plot on the other diagram. Very simple. No? Similarly, the second part also. Then some exercises. Again, diagram. The theory part is not yet finished, but some exercises are given. Module and argument exercises. See the question number 3. With a complex number given in Cartesian form, you'll be able to calculate the polar form by finding the modulus and the argument. Remember, plot the point on the Argand diagram and find out the module and the argument. You won't get every time the special angles. You have to use sometimes the calculator to get the angle. You get 59.5 and like that, likewise. These are some of the questions when the face-to-face session is start, I think we'll be able to do all the exercises. Online, there's no way to do these exercises. You have to try yourself, right? Remember, as I mentioned 1,000 times, following a degree, you have to have some certain self-learning part. That is finished. Not the now actually it is a new part. The exponential formula. Normally, if the class face-to-face session, we'll be discussing this one. Maybe the second or third week, maybe third day or fourth day, right? Second day or third day, we'll be discussing. I don't like to, discuss too much content in the first day. I think it's better to winding up this session rather than discussion some of those things. The exponential form. What is left? Remember what is left in this module: exponential form and conversion, exponential to other forms, other forms to exponential, conversion. Three forms, no? Cartesian, polar, and this one, exponential form. Engineering mathematics, very important part. After that, the square root of complex number and transform complex numbers. Very important. Remember, in semester 4, you have some modules, particularly those who are supposed to follow the multimedia, image processing, the matrix algebra, and the complex numbers. It will apply again, remember. I think Dr. Antunga do some of the modules. It has a lot of application in complex numbers and matrix algebra, particularly matrix multiplication and all that. The image transformation, image processing, the complex numbers also important. We discussed one of the things, the transformation of complex numbers. I think better to discuss in the next day. I don't like to too much. Can you understand what I am telling? Normally in the face-to-face session, we will be discussing these things. Maybe third day or fourth day, right? Still the first day, no? Right, even because it takes quickly we can go through because materials have been prepared. When I deliver the traditional manner, I use writing down everything on the board and I ask to write down the notes yourself. It takes long time, but here quickly we can discuss. It has the advantage, also disadvantage. I don't like to put lot of pressure on this yourself. Go through the whatever discussed so far. Remember, go through the whatever discussed so far, Cartesian form and the mathematical operations on the Cartesian forms, addition, subtraction, division, and the multiplication, and the complex conjugate, very important. Do some exercise. Better to do the exercise, all the exercise, and come with some, some confident knowledge to start this exponential form and the other thing. I think better to winding up this session rather than take another 20 minutes left. But I don't like to go through this other module. Is it okay now? I think are you having the hard copies of the material? Everybody having the hard copies?
Sir, we have hard copies, but some slides are missing on that complex number 2's PDF.
Yeah, good question. I have slightly modified some of the slides. I have modified some of the slides. The one you had is maybe different from the what I have presented. That's correct. What what I can do is I can mail it your common mail of that this particular two slides. The earlier I had the file called the work examples that has been deleted. Then all the content has been added to these slides because I just want because actually this material has been prepared for the face-to-face deliver early. The to online deliver, last moment I have to do some modification to the these files. If I send you a common mail, that is 2019 B1 ICT Google groups.com, it will bounce back. It doesn't work, I think. I can send you Mr. Bhatran send me your group mail, the multimedia software network separate groups. That will work, no? Shall I send to that mail those two files? Then you can get hard copies from that one. Is it okay?
Okay, sir, thank you.
Better to convey the message to the others also. I don't know, everybody can, I think everybody can hear, no? Better to know the, but after this lecture, I'll send those two files. Actually, those are modified files because once you are downloaded file, maybe slight difference. So there may be some exercise may be missing in there. You get the exact same material. Do the exercise first. Remember, do all the exercise first. and ready. We have some 1 week time now. Do all the exercise and thorough with what you have done so far. And right. Okay, so we winding up this session now. Hope to meet you on next Monday, right? Thank you very much.